Welcome to Module 1.4 Qubits and Quantum Gates. My name is Maximilian Rimbachrus and I'm currently a group leader at QTech at TU Delft. In this lecture we cover 4 topics. The first topic is quantum states, how to visualize 1 qubit and 2 qubit states. The second topic is quantum operations, how physics enables quantum computing. The third part is to focus in on 1 qubit quantum gates, how to visualize such operations. And the last topic covered in this lecture is 2 qubit gates and how they can generate entanglement. The first part of this lecture is covering quantum states. In order to understand quantum state, we first need to understand the superposition principle. A classical bit is either in the state 0 or in the state 1. It can either be or no. It cannot be it simultaneously. A quantum bit is special. It can be in both states simultaneously with an amplitude given by the parameter alpha 0 and in the other state with an amplitude given by the parameter alpha 1. The absolute norm squared of these 2 parameters needs to be 1 in order to be a physical state. If we now go from 1 qubit to a 2 qubit states, we need to add 2 more parameters to describe the state. These are the parameters alpha 0, alpha 1, alpha 2 and alpha 3. And all these describe the amplitude to capture one of the 4 possible basis states. Now, if we want to visualize a single qubit state, there's a very intuitive way to describe it. Remember back, a single qubit state is described by 2 complex parameters, alpha 0 and alpha 1, who have together the absolute square equal 1. If we now take out additionally the global phase, we can actually use a different representation of these 2 numbers. We can parameterize these 2 parameters in 2 angle parameters, theta and phi. And then we can actually visualize these 2 parameters on a surface of a sphere with norm 1, where theta describes the azimuthal angle and phi describes the polar angle. And all valid single qubit states live on the surface of this blosphere. If we now go from 1 qubit to 2 qubits, we have to add 2 additional complex parameters, alpha 2 and alpha 3. But in order to understand the 2 qubit state, the full 2 qubit state, we need to first understand what is the ket 00, what does it mean? Now, if we focus on only the first component, the ket describes with 2 indents. The first label is qubit 1 and the second label represents qubit 2. How does this mathematically look like? Mathematically, this kind of stitching together is described by the operation called a tensor product, which is a mathematical way to extend a 2 single qubit spaces to a 2 qubit space. There are 2 very different types of 2 qubit states. The first is the product state. The product state can be written as a direct tensor product between 2 single qubit states. One example is shown here, which is the state 0, 0. The opposite of a product state is an entangled state. An entangled state cannot be written as a tensor product of 2 single qubit states. One example is shown here, which is the state 0, 0 plus 1, 1. This state is called a Bell state and is a maximally entangled state. Entanglement will be a very important concept for many quantum algorithms, and you will learn in later lectures much more about it. In order to operate a quantum computer, we not only need states, but we also need to perform operations. For a quantum computer, the logical operations are called quantum gates. And the quantum gate is a time evolution. A quantum state involves in time described by a unitary matrix U. This time evolution follows from the physics of the system described by the Schrödinger equation. And the time evolution originates from the physical system behind and is described by a quantity called h. The unitary operation can then be represented as a matrix exponential of this operator h. Now, for n qubits, U is a unitary matrix of size 2 to the power of n times 2 to the power of n. Coming back from this abstract representation from the previous slide, how can we now visualize quantum operations? We will start here with single qubit quantum gates because these can be visualized as 3D rotations. And we will go over the most important and most common single qubit quantum gates you will encounter in the later lectures of this course. We will start with the X gate. The X gate is a 180-degree rotation around the x-axis. So you can visualize it by taking your state on the Planck sphere and rotate it by 180 degrees around the x-axis. The matrix representation of this quantum gate is 0, 1, 1, 0. If you look at this matrix, you also see it resembles the classical NOT gate. So the X gate is the classical, is the quantum analogy of the classical NOT gate. The second gate we will look at is the Y gate. The Y gate is a 100-degree rotation around the y-axis. Again, we take your state and we rotate around 180 degrees around the Y gate. The matrix representation is given here. And the Y gate is a gate which has no classical analogy because it also takes a phase gate into account. So additionally to a NOT gate, you also do a phase NOT gate. Coming back to a phase gate. The Z gate is a 180-degree rotation around the Z axis. The phase gate, what you can see here, is represented by the matrix 1, 0, 0, minus 1. So it flips the phase of the second state of your qubit. The second, there are further more important gates. One is the S gate. The S gate is a 90-degree rotation around the Z axis and is given by the matrix 1, 0, 0, I. And here comes in the complex nature of quantum bits. However, to get universal quantum computing, we need to add one more gate to this set. And the most commonly added gate to the set is the so-called T gate. The T gate is a 45-degree rotation around the Z axis and is given by 1, 0, 0 e to the I pi divided by 8. The last gate we want to introduce is the H gate or the Hadamard gate. This gate is of special importance and integral part of many quantum algorithms because it creates a superposition state, a maximally superposition state from a basis state. And this state can be represented as a 180-degree rotation around the XZ axis. So it's not a principal axis and the rotation is tilted. So going from 1 qubit to 2 qubit quantum gates, how can we visualize these gates? The first very important concept is 2 qubit quantum gates can entangle the qubits. In order to see this, we first look on the simplest 2 qubit gate, except the trivial gate doing nothing, the identity gate. This is the so-called swap gate. The swap gate, which is a classical gate, just swaps qubits 1 and 2. And if you look at a truth table, we can see that the state 0, 1 is swapped to the state 1, 0, and the state 1, 0 is swapped to the state 0, 1. If we write this now as a matrix form, we get the following matrix as represented here on the side. The swap gate is a non-entangling gate. So in order to get entangled, we need so-called conditional gates. Similar to a controlled NOT gate from the classical, we can also get here controlled rotation gates. And these controlled rotation gates can actually entangle the two qubits. The controlled rotation gates have the following truth table, where we replace the question marks later with the correct parameters, and has the following matrix form. If your first qubit is in the state 0, nothing happens. Only if the first qubit, the so-called control qubit, is in the state 1, we perform an interaction. The simplest of these gates is the CNOT gate. Here, the controlled gate is the X gate. So controlled on the first qubit, we perform an X gate, a NOT gate on the qubit 2. And the matrix form is given here. It has a 0, 1, 1, 0, and the later in the lower block in the matrix. However, we have seen there are many rotation gates on the previous slide. This means we can also construct more controlled gates. And I will now go through the most important for these lectures. The second controlled gate we will look at is the so-called CZ gate. The CZ gate performs a phase flip if the first qubit is in 1. The nice thing about this gate is it does not change the probabilities of the state. It only provides a conditional phase dip depending on the first state. Like the CNOT gate, this is also a gate which can generate entanglement. There's one last gate we also need to look at, and this is the CZ gate. This gate is of special importance because it's a so-called non-Clifford gate. And this gate can be used to create a so-called Toffoli gate, a 3-qubit gate which is an integral part of many quantum algorithms. In this lecture, you should have learned 4 concepts. The main takeaways of this lecture are: quantum gates come from the physical system and are described by a matrix. The size depends on how many qubits it acts on. Single qubit gates can be represented as rotations. Additionally, single qubit gates can bring a qubit in a superposition state, and this is, for example, performed here by the Hadamard gate. And lastly, 2-qubit gates can entangle 2 qubits with each other, which means they cannot be described by a tensor product state anymore. With this, I want to conclude this lecture, and I thank you for paying attention to this lecture, and I wish you a good journey for the remaining of this course.